Physics. Topic: Moving charges and magnetism. Magnetic field. We know that a magnetic force is felt around a magnet, which is called magnetic field. In 1820, an experiment conducted by Danish physicist Hans Christian Ørsted demonstrated that electric currents also create magnetic fields. So moving electric charges or current always generate a magnetic field in the space surrounding the wire, a principle described by Ørsted's discovery in the right-hand rule. Magnetic fields and their shape can be visualized using magnetic field lines. Magnetic field lines are imaginary lines used to represent the direction and relative strength of a magnetic field at any point in space. The magnetic field lines point from the North Pole to the South Pole in a magnet. Magnetic field lines in a current-carrying wire are circular rings. Magnetic field lines are parallel straight lines inside a current-carrying solenoid. Biot Savart law. It's actually a mathematical equation. We know there is a magnetic field around a current-carrying conductor. Biot Savart law is used to calculate this magnetic field produced by a small segment of the conductor. It is used to understand the magnetic field created by different types of conductors, such as straight wires, loops, and coils. Magnetic field is represented by the letter B, and dB is the differential of that magnetic field. The equation form of Biot Savart law is dB equals mu0 into IDL sine theta divided by 4 pi r squared. Let's do a problem to understand it. A circular coil of radius 5 cm has 100 turns and carries current of 3 Ampere. Find magnetic field at its center. Formula for magnetic field at center of circular coil with n turns is B equals mu0 Ni by 2r. Substituting the given values, we get the answer as 3.768 into 10 raised to minus 3 Tesla. So the answer is 3.77 millitesla. The Biot Savart law is about finding magnetic field at a point. Ampere's law is about finding magnetic field due to total current. Ampere's law says that the total magnetic field around a closed loop depends on the current flowing inside it. The formula is derived from the statement that the line integral of the magnetic field B around any closed loop is equal to mu0 times the total current passing through the surface enclosed by that loop. Also, the formula for the magnetic field due to infinite straight wire and magnetic field inside solenoid is found using Ampere's law. Let's do a problem to find magnetic field inside solenoid. N equals 500 turns. Length equals 25 centimeters. Total current is 3 Ampere. The N turns per unit length is found to be 2000 turns per meter. The magnetic field is calculated to 7.54 millitesla. Lorentz formula explains phenomena like the motion of charged particles in magnetic fields. Assume a charge moving in a magnetic field. Say an electron moves with velocity 5 into 10 raised to 6 meter per second, perpendicular to a magnetic field of 0.2 Tesla. To find the force on it, we use Lorentz force formula that explains force on a moving charge in a magnetic field, which says F equals QVB sine theta. Formula is different if the charge is in combined electric and magnetic fields. A sample problem with solution is given. We learned about the force on a moving charge. Now let's see the force on a current-carrying conductor with length L and magnetic field B. The formula is F equals I into L into B. The formula for force between two parallel current-carrying conductors separated by distance d, carrying currents I1 and I2 is also given. Let's do a problem on the force between two parallel current-carrying conductors. Two parallel wires 10 centimeters apart carry currents of 3 Ampere and 4 Ampere in same direction. Find force per unit length. The answer is 2.4 into 10 raised to minus 5 newtons per meter. Torque on current loop in magnetic field. A current-carrying loop placed in an external magnetic field experiences a twisting force, torque, that tends to rotate it. The magnitude of the torque is tau equals IAB sin theta, where I is the current, A is the area of the loop, theta is the angle between the normal to the loop, and vector B if the loop have n times. Torque equals NIAB sin theta. Magnetic dipole moment. Definition. It measures the strength and direction of the magnetic field produced by the current loop. Formula. M equals I into A. where I is the current and A is the area enclosed by the loop. Current loop as magnetic dipole. A current loop behaves like a magnetic dipole. Formula. For multiple loops, coil, M equals N into I into A for N turns. A moving coil galvanometer is a fundamental instrument used to detect and measure small electric currents. Current sensitivity is defined as the deflection produced in the galvanometer per unit current flowing through it. Formula for current sensitivity equals NAB divided by K. To increase sensitivity we can increase N, number of turns, increase A, coil area, increase B, magnetic field, decrease K, softer spring. A galvanometer can be converted to ammeter. The purpose is to measure larger currents than the galvanometer can handle. Method is to connect a low resistance resistor called shunt resistor, S, in parallel with the galvanometer, G. The shunt diverts most of the current, allowing only a small, proportional current through the coil. The formula for the shunt resistance is given. A galvanometer can be converted to voltmeter. The purpose to measure larger voltages. The method is to connect a high resistance resistor R in series with the galvanometer. The formula for the high resistance resistor is given. Let's do a problem. A galvanometer is converted to voltmeter. We have to find the resistance required. From the given values and using the formula, the resistance required to convert galvanometer to voltmeter is calculated to 1950 ohm. Video by Anand Mohandas.